Welcome to Earthly Teachings, where learning is clear and powerful. Today we are working on Mathematics N6. Let's learn together. In this video, we'll dive into solving a powerful type of equation, non-homogeneous linear differential equations with constant coefficients. Our main goal is for you to be able to find the complete solution to these equations, which will involve combining two distinct parts. The first part is called the complementary function, which we'll denote yc. And the second part is called the particular integral, or yp. By the end of this tutorial, you'll have a clear step-by-step procedure to tackle any problem of this type. First, let's understand the two main components of our solution. This is a very important concept to grasp. Consider a general linear second-order differential equation. A times the second derivative of y plus b times the first derivative of y plus c times y equals f of x. This equation is non-homogeneous because the right-hand side, fx, is not equal to 0. If fx were 0, it would be a homogeneous equation. The complete solution to this type of equation is not a single part, but a combination of two solutions working together. The complete solution is y equals yc plus yp. Let's define these two parts. The first part, y bar c, is called the complementary function. To find it, you solve the related homogeneous equation, which means setting the RHS to 0. In other words, yc is the solution to a d2i dx2 plus bdiac plus cix0. The complementary function always contains arbitrary constants. It represents the general behavior of the system described by the differential equation without any external forces or inputs. The second part, yip, is called the particular integral. It is a specific solution that satisfies the full, non-homogeneous equation with the given fx. Importantly, the particular integral never contains any arbitrary constants. It represents the steady-state response of the system due to the specific forcing term fasos x. Think of it this way. Complementary means completing. The complementary function completes the particular integral to give the full picture. The general solution, yc plus yip, is the complete picture. Now that we understand the two parts of the solution, let's outline the full procedure for solving these differential equations. The process can be broken down into 6 clear steps. Step 1 is to find the complementary function. This always begins by forming the auxiliary equation and finding its roots. Remember, to do this, you replace the second derivative with r squared, the first derivative with r, and y with 1, then set it to 0. Step 2 is to use the roots from the auxiliary equation to write down the form of yc. The form of yc depends entirely on whether the roots are real and different, real and equal, or a complex conjugate pair. We'll cover this in more detail with examples. We're going to continue with our procedure, focusing on the second step, finding the form of the complementary function. The auxiliary equation we formed is a quadratic equation, which means it will have two roots. These roots, which we'll call r, determine the structure of our complementary function, yc. There are 3 possible cases for these roots. Case 1. The discriminant, b squared minus 4ac, is positive, giving us 2 different real roots, r1 and r2. In this situation, the complementary function is a times e to the r1x plus b times e to the r2x. Case 2. The discriminant is 0, giving us a single repeated real root, r. For this case, the complementary function is e to the rx, all multiplied by a plus bx. A common mistake here is to forget the x in the second term. If you just write a plus b, it's not a general solution. This x is essential for the second part to be linearly independent. Case 3. The discriminant is negative, resulting in a pair of complex conjugate roots. We can write these as alpha plus or minus I times beta. The complementary function takes the form e to the alpha x times a cosine beta x plus b sine beta x. Here, alpha is the real part of the root, and beta is the imaginary part. It's a key exam strategy to make sure you correctly identify alpha and beta from your roots before substituting them into the formula. Now let's move on to step 3, finding the particular integral yip. This step is about making an educated guess. The trial solution for y equals p depends entirely on the function fx on the right-hand side of the original differential equation. This is a very important rule to remember. There are several common forms we'll encounter. If f as x is a constant, like the number 5, we assume a particular integral that is also a constant, which we'll call c. If fx is a linear polynomial like 2x plus 3, we assume y to p is a general linear polynomial, cx plus d. Notice we include the constant term d even if fx only has an x term. Similarly, if fx is a quadratic polynomial, we assume yp is a general quadratic polynomial, cx squared plus dx plus e. Again, we include all terms from the constant up to the highest power x squared. This is a critical strategy. Always assume the full polynomial form for yp, not just the terms that appear in fe. Forgetting to do this is a very common error. The logic here is that differentiating a polynomial produces a polynomial of the same or lower degree. By starting with the highest degree in fx, we ensure our assumed yp has enough terms to balance fx in the equation. Now, let's look at a special case for the particular integral, when fx is an exponential function. The rule for exponential x is a bit more complex. If fx equals a times e to the power of bx, we start by assuming yp is c times e to the bx. This assumption, yp equals ce to the bx, works, but it comes with a very important condition. You must check if the term e to the bx is already part of your complementary function, wasai. This is what we call the duplication rule. Think about it this way. If your yp is already a solution to the homogeneous equation, it will differentiate to 0 on the left side, leaving nothing to balance the fx on the right side. It would be a futile guess. So, if the term e to the bx is not in yc, our assumption is correct. The particular integral is simply c times e to the bx. However, if the term e to the bx is part of your complementary function, you have to modify your guess for yp. You do this by multiplying your assumption by the independent variable x. So, the new correct assumption for the particular integral is c times x times e to the bx. This is a critical rule to remember and apply correctly. We've made it through the first 3 steps. We have our complementary function, we see, and we have a trial form for our particular integral yrp. Now we can execute the next step in the procedure, differentiation and substitution. Our goal in step 4 is to determine the unknown constants in our trial yp like c, d, and e. The process is straightforward. First, take your assumed particular integral yp and differentiate it twice to find its first and second derivatives. Next, you will substitute this trial solution along with its derivatives back into the original non-homogeneous differential equation. Remember to use the full equation, including the fx on the right. This substitution will result in an equation that must be true for all values of x. To make it true, we use the method of equating coefficients. Step 5 is about bringing everything together to form the general solution. The complete general solution, which we'll simply call y, is found by adding your complementary function yc to your now complete particular integral yct. That's it. This general solution contains arbitrary constants from yc, like a and b. It describes a family of solutions, not a single one. There is one final step you might need to take, and that is to find a particular solution. This happens when the problem gives you extra information, which we call initial or boundary conditions. These conditions allow us to move from the general solution, with its arbitrary constants a and b, to a single specific solution. A typical set of conditions for a second-order equation might look like this. Y of 0 equals 1, and y prime of 0 equals 2. The first condition tells you the value of the function y at x equals 0. The second condition tells you the value of its derivative, dx, at the same point. So how do we use these? It's a 2-part process. First, take the first initial condition and substitute the values of x and y into your general solution. This will give you an equation involving a and b. Second, differentiate your general solution with respect to x. Then substitute the second initial condition, the values for x and dx, into this new derivative equation. This will give you a second equation for a and b. You now have a system of 2 linear equations with 2 unknowns, a and b. Solve this system to find the exact values of a and b. Once you have them, substitute them back into your general solution to get the particular solution. It's time to put our procedure into practice. Let's tackle example 422 from your notes. The problem asks for the general solution to the differential equation. The second derivative of y minus 3 times the first derivative of y minus 10y equals 5. As always, we begin with step 1, finding the complementary function. This means solving the related homogeneous equation, which is d2y dx2, 3dy t 0. The auxiliary equation is r squared minus 3r minus 10 equals 0. We can solve this by factoring. It factors into r minus 5 times r plus 2 equals 0, which gives us two distinct real roots, r equals 5 and r equals negative 2. Using case 1 from our procedure, the complementary function is a times e to the 5x plus b times e to the negative 2x. Excellent, we've completed the first step. Now for step 2, the particular integral. We look at the RHS of the original equation. The right-hand side, f of x, is simply the constant 5. Following our rules for finding y at p, we assume a particular integral of the form yp equals a constant c. There's no e to the bx term to check for duplication, so our assumption is correct. Now we find its derivatives. The first and second derivatives of a constant c are both 0. This brings us to step 3. Substitute our yp and its derivatives back into the original equation. Substituting gives us 0 minus 10 times c equals 5. This simplifies to negative 10c equals 5. Solving for c, we find that c equals negative 1/2. Therefore, our particular integral is negative 1/2. The final step is to combine our two parts. The general solution y is the complementary function plus the particular integral. The general solution is y equals a times e to the 5x plus b times e to the negative 2x minus 1/2. Let's compare this to the memo. The memo gives the general solution as ae5x plus b2x 1/2. Our answer matches perfectly. Notice the memo did not use c for the constant in YP to avoid confusion with the c in YC. It just jumped to the value. Either is acceptable. Great work! Let's move on to example 423. This problem takes our procedure one step further. We need to find the particular solution of d2y/y dx2, dx 6ix12, subject to the conditions that y of 0 equals 1 and the first derivative at 0 equals negative 1. This means we'll need to find the specific values for the constants a and b. As before, we start by finding the general solution. The process for yc and yp will be identical to the last problem. For the complementary function, the auxiliary equation is r squared minus r minus 6 equals 0. This factors into r minus 3 times r plus 2 equals 0, giving roots r equals 3 and r equals negative 2. So the complementary function is yt equals ae to the 3x plus be to the negative 2x. For the particular integral, the RHS is a constant. Chapter 12. We assume yp equals c. Its derivatives are both 0. Substituting into the original equation gives negative 6c equals 12. The general solution is the sum, y equals ae to the 3x plus be to the negative 2x minus 2. Now for the new part, using the initial conditions. This is step 6 from our procedure. The first condition is y of 0 equals 1. We plug x equals 0 and y equals 1 into our general solution. This gives us our first equation for a and b, a plus b equals 3. For the second condition, we first need to differentiate our general solution to find di dx. Now, we use the condition di ex at 0 equals negative 1. Substituting gives negative 1 equals 3a minus 2b. We now have a system of two equations. Let's solve them. From the first equation, we can write b as 3 minus a. Substituting this into the second equation gives negative 1 equals 5a minus 6. Solving for a, we find a equals 1. Substituting back into b equals 3 minus a, we get b equals 2. Our final step is to substitute these specific values of a and b back into our general solution. This gives us the particular solution. Y equals e to the 3x plus 2e to the negative 2x minus 2. Comparing our answer to the memo, we see that it is exactly the same. We have successfully found the unique solution that satisfies both the differential equation and the given initial conditions. This is a complete and powerful solution. In our next example, we'll see how to handle a quadratic polynomial on the right-hand side. This is example 4.4. We need to find the general solution of d squared y by dx squared minus dy by dx minus 6i equals x squared plus 6. The presence of x squared on the RHS tells us this will be a polynomial case. Let's first find the complementary function yc. The auxiliary equation is r squared minus r minus 6 equals 0. This factors into r minus 3 times r plus 2 equals 0, giving roots r equals 3 and r equals negative 2. Therefore, our complementary function is y(t) equals a e to the 3x plus b e to the negative 2x. Now for the particular integral yp. We examine the RHS x squared plus 6. This is a quadratic polynomial. Following our rule, we assume a general quadratic polynomial for yp. This is a very common place for students to make mistakes by only assuming yp is cx squared. Remember to include all lower-order terms. Next, we find the derivatives of this assumed yp. The first derivative is 2cx plus d, and the second derivative is 2c. Now we substitute these into the original differential equation and equate coefficients. Substituting gives us 2c minus the quantity 2cx plus d, minus 6 times the quantity cx squared plus dx plus e, and all of this equals x squared plus 6. Expanding and collecting like terms, we get negative 6cx squared plus negative 2c minus 6dx plus 2c minus d minus 6e. This must equal 1x squared plus 0x plus 6. By equating the coefficients of x squared on both sides, we get negative 6c equals 1, so c equals negative 1/6. Equating the coefficients of x, we get negative 2c minus 6d equals 0. Plugging in our value for c, we get d equals 1/18. Finally, equating the constant terms, we have 2c minus d minus 6e equals 6. Solving for e gives us negative 115 over 108. The algebra can be a bit tedious, so be careful and methodical. Now we have our complete YA. The general solution is the sum of yc and yp. Notice how the quadratic part from fx is reflected directly in the yp term of the final answer. Comparing with the memo, our solution matches. Our next example, 4.5, is a great one because it reinforces a key principle about choosing the particular integral. We need to find the general solution of 3d2y dx2 plus 2d dx y equals x. The RHS is a simple x. The auxiliary equation is 3r squared plus 2r 1 equals 0. Factoring gives 3r minus 1 times r plus 1 equals 0. This gives us real, distinct roots. R equals 1/3 and r equals negative 1. So the complementary function is yt equals ae to the 1/3 x plus be to the negative x. Now for the particular integral ypp, look at the RHS f of x equals x. This is a linear polynomial. Our rule states that for a linear f, say, we must assume the general linear form for yp, cx plus d. A common pitfall is to only assume yp as to cx because there is no constant on the RHS. You must include the constant d. The derivatives are dx equals c and dt x2 equals 0. Now we substitute into the original equation, 3 plus 2c, cx plus d equal x. This simplifies to 2c minus cx minus d equals x. Now we equate coefficients. Let's compare the coefficient of x on both sides. We have negative c equals 1, which means c must be negative 1. This is a crucial step to avoid errors. Next, we compare the constant terms. 2c minus d equals 0. Since we know c is negative 1, we can solve for d. 2 times negative 1 minus d equals 0, which gives d equals negative 2. So, our particular integral is yep equals negative x minus 2. The general solution is the sum, y equals ae to the 1/3 x plus be to the negative x minus 2. Once again, our solution matches the memo exactly. This problem perfectly illustrates why you must include all lower degree terms in your trial particular integral. For our final example, 4.26, we'll encounter a complex complementary function and a quadratic particular integral. We need to determine the general solution of d2y dx2 plus 8i equals x squared. This combination will test our understanding of both cases. Let's begin with the complementary function yc. The auxiliary equation is r squared plus 8 equals 0. Solving for r squared, we get negative 8. Taking the square root, r is plus or minus the square root of negative 8. We can write the square root of negative 8 as the square root of 8 times the square root of negative 1. This simplifies to plus or minus 2 root 2 times I. These are complex conjugate roots of the form alpha plus or minus I beta. Here the real part alpha is 0, and the imaginary part beta is 2 root 2. Using our formula for complex roots, y2y equals e to the 0x times a cosine 2 root 2x plus b sine 2 root 2x. Since e to the 0 is 1, our complementary function is simply a cosine 2 root 2x plus b sine 2 root 2. Now for the particular integral y of p, the RHS is fx ex squared. This is a quadratic polynomial. Our rule tells us to assume the general quadratic form for y equals et, cx squared plus dx plus e. Once again, it is essential to include all terms, including dx and e, even though the original fx only has an x squared term. The derivatives are dx equals 2cx plus d and d2i/dx2 equals 2c. Now we substitute into the original equation and equate coefficients. Watch out, the first derivative term b ddx is missing from the original equation. Its coefficient is 0. Substituting gives 2c plus 8 times the quantity cx squared plus dx plus e equals x squared. Expanding, we get 8cx squared plus 8dx plus the constant term 2c plus 8e. This must equal 1x squared plus 0x plus 0. Equating coefficients of x squared, we get 8c equals 1, so c is 1/8. Equating coefficients of x, we get 8d equals 0, so d is 0. And equating constant terms, 2c plus 8e equals 0. Plugging in c equals 1/8 gives e equals negative 1/32. So our particular integral is y-qp equals 1/8 x squared minus 1/32. The general solution is the sum of our y-qp and y-qp. As you can see, our answer matches the one provided in the memo. We've covered a lot today. Let's quickly recap the powerful method we've learned for solving non-homogeneous second-order linear differential equations. We saw that the complete solution, y, is a sum of two parts, the complementary function, yc, and the particular integral yp. The complementary function, yc, is the general solution to the associated homogeneous equation, where the RHS is set to 0. Its form depends entirely on the roots of the auxiliary equation. The particular integral y to p is a specific solution to the original non-homogeneous equation. Its form depends on the nature of the RHS function, phex. For polynomials, you must assume a general polynomial of the same degree. For exponentials, remember the duplication rule. The systematic process of setting up the trial y of p, differentiating it, substituting it back into the equation, and then equating coefficients is a reliable way to solve for your unknown constants. It's an exam writing strategy that will serve you well. Don't forget the final step. If you're given initial conditions, use them to find the unique particular solution by solving for the constants in your complementary function. Remember to speak slowly and be confident in your calculations. Taking your time, checking your work, and understanding why each step is taken will lead to success. Now you are able to find the complete general solution of non-homogeneous linear differential equations. Thank you for watching. Like, subscribe, and continue learning with earthly teachings. See you next time. Thank you for watching. Like, subscribe, and continue learning with earthly teachings. See you next time.